We're going to move on to a completely different topic here, which is wavefront. We're moving out of the topography of the cornea, and indeed we're no longer dealing with the optics of just one part of the eye, but the optics of the entire eye. Now, those of you who have completed the optics course, the 20 lectures on optics, know how I discuss vergence. I discuss vergence as if it's an abstract number that gives the location of where the rays of light converge. So that if we have a vergence of, let's say, minus 10, minus means that the rays of light converge to the left, and 10 means that they converge at 1/10 of a meter. We're going to approach vergence in a less abstract way now, and I'm going to present to you an alternative way of thinking about vergence, and we're going to do it with this diagram here. This diagram shows the retina, let's say just the posterior pole, that's on the left-hand side of the slide. And we see rays of light emanating from a single point on the retina. They're diverging. And we don't usually think of rays of light coming out of the retina. Of course, we think of rays of light going into the retina. But every time that we examine someone else's eye with a direct and indirect 78 diopter lens, of course, we're illuminating the retina, and as such, every point in the retina that we can see has photons coming out of that point, diverging, coming out of the eye, so that we can image the retina on our own eyes or on our cameras or whatever it is that we're using. So this is an example in this slide here of a retina that we're illuminating, and we're looking at rays of light coming off of the patient's retina. Now, the rays of light come off from a single point, and we see our familiar vergence lines here, which are lines that start out at a single point, as opposed to ray tracing lines, which don't. Anyway, these are vergence lines. And let's say that our first landmark coming off of the retina, the first spot that you see to the right, let's say that that's 1 millimeter from the retina, or 1,000th of a meter from the retina. So from that point, rays of light are converging 1,000th of a meter to the left. What does that mean in vergence terms? What's the number that we're going to get? Well, the rays of light are converging to the left. That means that the sign of the vergence has to be minus. And 1,000th of a meter means that it is 1,000 diopters. So at that point, we're at minus 1,000 diopters, minus 1,000 for the vergence. Now, imagine what this cohort of photons looks like. Let's say that this cohort of photons, this group of photons, came off of the retina instantaneously from this one point. They're going to form a front that is moving forward in the eye. And I ask you, what does the shape of that front, that light wave front, that cohort of photons, what shape do they describe? And the answer, of course, is that they describe a sphere, or a section of a sphere, like a little bubble that is coming off of the patient's retina, this little bubble of photons. And I ask you to think about what the curvature of that bubble is. Well, when that bubble is 1,000th of a meter from the retina, they describe a portion of a sphere that has a radius of curvature of 1,000th of a meter. They describe a section of a sphere that is very highly curved. Okay, let's look at the next line out. Let's say that that next landmark to the right is 3 millimeters from the retina. So what's the vergence here? It's not minus 1,000, it's minus 333. I'll let you do the math on your own. You can figure it out. Since the cohort of photons at this point describes a section of a sphere with a larger radius of curvature, 3 times the radius of curvature. The radius of curvature now is 3 millimeters rather than just 1. The curve of that sphere is much more gradual. It's a much flatter sphere than the sphere with a radius of curvature of only 1 millimeter. So we can look at the vergence here, not in terms of the rays of light that we've drawn that are emanating from the point, but we can look at the vergence as a description of the degree of curvature of that cohort of photons. So that a lower vergence means less curve to that front, that wavefront. And you can think of the traditional vergence lines that we've drawn, those that come from a point, as being at every point orthogonal or perpendicular to this wavefront. Anyway, the photons come off of the retina, they form this perfectly shaped section of a sphere, and they encounter the patient's lens, and the lens has a plus power, and these are diverging rays of light. In terms of the vergence, they represent this convex wavefront that's coming off of the retina, and they strike this plus lens, and the plus lens makes them less divergent, but incompletely so. So they come off of the lens, and they're still diverging slightly. The wavefront is still a bit concave, and then they come out of the cornea, and if this is an emmetropic eye, then they're going to come out of the cornea with a planar wavefront. And we know that because the vergence lines that we're used to drawing, they're all parallel because we've got a vergence of 0 coming out of this emmetropic eye. And I know you can see why it has to be a vergence of 0. And these vergence lines that we draw, if we say they represent the perpendicular, then what are they perpendicular to? Well, they're perpendicular to a planar wavefront. However, that's the case only in the ideal eye. In the real eye, each optical element through which this cohort of photons passes distorts the wavefront. Now, we're used to thinking of the speed of light as being a constant. C, we're told that the speed of light is invariant. It's a fixed thing in nature. Einstein taught us this. Well, that's kind of true. The speed of light is invariant. It is absolutely fixed. It's c in a vacuum. However, when light passes through a medium, it's impeded. It's retarded in its flow. And it passes through the medium, as long as it's not a vacuum, at some speed less than c. And the degree to which the movement of light is retarded is described by the index of refraction of the medium, where a higher index means that the light is slowed down more. Well, the index of refraction of any medium in the real world is not completely uniform. The medium's lumpy. There are parts of the lens that are maybe cataractous. Even if there aren't parts that are cataractous, there are parts where the n is a little higher, a little lower. The result is that this cohort of photons passing through the lens, this march of photons going through the lens is distorted, with some of the photons moving through at a faster pace than other photons. And the result is that the wavefront coming out of the lens, and then even more so the wavefront coming out of the cornea, is distorted, and it is not completely planar. So the ideal wavefront in this diagram is drawn in black. The real wavefront, the real aberrated wavefront, is drawn in red. Now, who cares to measure what the aberrations are coming out of the eye? What physiologic value, what clinical value does this have for us? Well, it doesn't have any, but the wavefronts, the description of the wavefront of the rays of light coming out of the eye are, of course, identical to the description of the distortion of rays of light coming into the eye, the description of the wavefront going into the eye. If the eye is presented with an ideal planar wavefront, that planar wavefront will be distorted, aberrated in the same way going into the eye. So the patient looks at Sirius, at the dog star up in the sky, and the rays of light coming from the dog star, of course coming with a 0 vergence, they're coming with this perfect planar wavefront. Well, perfect if we were out in space, but humor me. And they strike the eye, and the imperfections in the eye produce an aberration to this wavefront. So we're interested now, going forward, in measuring what the aberration is. How are we going to do that? Okay. We're going to create an aberrometer. It's going to be very simple. And we're going to do it again by illuminating the retina and looking at rays of light coming out of the eye and measuring the aberration of the wavefront coming out of the eye, because that's a description of the aberrations that are going to be produced going into the eye. We're going to illuminate the retina, and the rays of light are going to come out of the eye. And if it were an emmetropic, absolutely perfect eye, the rays of light would all come out absolutely parallel. But I represent to you that because of distortions, aberrations in this wavefront, that the photons are not all going to be parallel. Some of them are going to be a little bit diverging, some are going to be a little bit converging. But for a second, let's picture the perfect eye, where the rays of light are emanating from the cornea, coming out of the cornea, absolutely perfectly parallel. We're then going to introduce in front of the eye a little cardboard disc, an opaque cardboard disc. And into this cardboard disc, we're going to perforate little holes. And we're going to make the holes in a grid pattern, and they're going to be absolutely perfectly equally spaced. Now, let's say that they're spaced out so that the holes are separated by 1 millimeter. In actual fact, we'd of course make them much more closely spaced than this. But let's say that they're exactly spaced by 1 millimeter. If the rays of light striking that disc are perfectly parallel, then if we put, let's say, a little piece of black paper on the side of our disc with the apertures, on the opposite side from the eye, then we'll produce little tiny pinpoints of light on this sheet of black paper as the photons pass through this disc with a little 1 millimeter spaced grid of holes. And what will the pattern be on that black sheet of paper? Well, not only will it be a regularly spaced little white dots, but in fact that spacing will remain 1 millimeter separated. We're going to produce a grid that's identical not only in pattern, but in actual spacing, in actual measurement, to the pattern of apertures on the disc. Now, imagine that this were not an emmetropic eye, but a myopic eye. And if we illuminate the retina in a myopic eye, then the rays of light are going to emerge from the eye converging. You can think about it for a second. Think about how the far point works, why they must be coming out of the eye converging. Anyway, the front of the eye has too much plus power. Plus is going to make them converge. There are a lot of ways to think of this, but you realize that the rays of light are converging. Now, if those converging rays of light pass through our little piece of cardboard with the 1 millimeter spaced apertures, what will the pattern be projected on that little black sheet of paper? Well, this is an ideal myopic eye, so they're still all going to be equally spaced, but will they be more closely packed or more spread out than the 1 millimeter grid on the disc that is between the eye and this black sheet of paper? Given a little bit of thought, you should see that the little spots of light will be more closely spaced. They're more closely spaced because the rays of light passing through each of these holes is converging, and they'll converge towards this black sheet of paper, and the result is that the pattern, although regularly spaced, will be more tightly packed, and similarly with a hyperopic eye, will be more spread out. This is an example of a device that might produce such a measurement, and the only thing that you see here that's different from what I've described is that there's a beam splitter to illuminate the eye in a coaxial fashion. Well, there is one other thing, which is this. The little sheet, that little cardboard with the apertures in them, what we're going to do, the thing that distinguishes this as a Hartmann-Shack aberrometer, I know in this slide, unlike subsequent slides, it says Shack-Hartmann aberrometer as opposed to Hartmann-Shack. I imagine this slide was produced by Dr. Shack and not Dr. Hartmann. That in the little apertures in that piece of cardboard, we're going to introduce lenses. We're going to introduce ads. And let's say that rather than a black sheet of paper, we've got a CCD because we're very fancy. Let's say that CCD is 1/10 of a meter from the cardboard disc with the apertures into each aperture. We're going to put a little +10 lens so that the rays of light passing through each aperture will converge to a point. Now, the only reason that we're doing this is to make the little pinpoints of light on the CCD more precise, smaller, so that it facilitates more precise measurement between the spots. But that that doesn't change the optics. It's just to aid in getting a measurement with the CCD. So this is an example of what an aberrated wavefront would do. We're no longer dealing with the ideal ametropic or even ideal myopic or hyperopic patient, but a wavefront that is in parts myopic and in parts hyperopic, in parts converging and in parts diverging. And you can see the result is going to be that everywhere that the wavefront is converging, the image on the CCD is going to be of dots that are more closely packed, and everywhere that the rays of light are diverging, the little dots of light are going to spread out. And this is going to give us a sense of the wavefront, the aberration in the wavefront. This is an example. The ideal is shown at the top with the little lenslets, and at the bottom you can see it's all cocked. Okay, see Hartmann-Shack aberrometer. This slide was undoubtedly produced by Dr. Hartmann. We know that a trick question we always ask, what's the most important optical element in the eye? Well, if you want to be a smartass, it's the tear film, it's not the cornea. But you can see this in this slide, that disruptions in the tear film will greatly aberrate, if that's a word, the wavefront on the left. More interesting is the slide on the right, where you see centrally the little dots are very, very closely packed, indicating that there's a part of this wavefront that is very myopic, and around that, the little dots are much more spread out, and this is a part that is relatively hyperopic. And the slide is labeled as keratoconus, and it could be. I mean, certainly one would expect keratoconus to produce a pattern like this. But unlike topography, which we've dealt with up until this point, when we are looking at wavefront, we get the total distortion produced by the total optics of the eye, but we cannot say for certain which part of the eye has produced the aberration. So we're given that this is keratoconus, fine, I'm sure that it is. But in general, when you look at an aberration, you cannot say which optical element in the eye produced it. This is an example of a commercial aberrometer. It's a Topcon aberrometer, and I know it shows topography on the bottom. That's fine. You can see the little dots shown in the middle slide on the right. Now, I don't know if those dots represent the cornea that's shown at the bottom, but if they do, then you get the sense, just as when we were trying to judge degree of cylinder with a placido disc, that you can't really look at an array of dots and derive from that, visually on your own qualitatively what's going on with the wavefront, unless the distortion is just tremendous.